Now, in introduction, the main motivation of this work is solar energy harvesting, and the technology that we will be presenting today is photo-electrochemical water splitting. Very briefly, a cartoonistic view of what happens is that when solar light is absorbed by semiconductor, then an electron-hole pair created. And then if this material has an interface with a liquid, let's say water or any aqueous solution, the purpose is to water splitting to make hydrogen. So this is mostly water with some acidity or basic properties, depends on what is the nature of the electrolytes. And these two dotted lines are the hydrogen and oxygen reduction potentials. For a proper hydrogen or water splitting reaction, this chemical energy or this reduction energy level should be below the conduction band minima, and this oxygen reduction potential should be above the valence band maxima. What happens if these criteria are met, an electron and hole pair get created, then hole can perform this part of the reaction where we have some hydrogen or protons basically, and some oxygen molecules. And then the electron, on the other hand, travel through the external circuit, come via the another electrode to perform the hydrogen side of the reaction, where then we get hydrogen molecule. And then, of course, there are membranes sometimes in the middle, or this can be separated into two different subsystems, and the gases can be collected separately. Now, the main point or main feature of this work is to focus on this material which perform this water splitting reaction. This is the solar absorbing material, like solar light absorbed in here. It is also called photo-electrocatalyst. There are some key properties that needs to be maintained for an efficient hydrogen production via water splitting. Those requirements are, for example, appropriate bandgap. What it means by that, this water splitting minimum energy that is needed is about 1.23 volt. Hence, the band gap of the material should be above 1.23 electron volt. Usually, because of the overpotential, it is recommended that it should be around 2 electron volt. The second is separation of photo-excited electron and hole pairs. What it means that once the electron and hole pair is created, let me use my laser pointer. Once these two are created, then there is always a possibility that these two recombine, and hence no free carriers are available. And this recombine can happen within a picosecond level. So we need to break the pair. This is called exciton pair. If they still see each other interact, we need to break the exciton to have an efficient free carriers. Usually materials which has a higher dielectric constant, they have lower exciton binding energy. So that helps, and also some other inbuilt electric field like PN junction kind of technology is also used, like in photovoltaics. And the third thing is the charge transport, meaning once you separate the carrier, the charge should be efficiently transported through the materials up to the interface, up to the solid liquid interface. Now, today's work is basically focusing on the third part, the charge transport part, on metal-oxide photo-electrocatalysts. The point that we will be focusing today is polaron. In metal-oxide, especially in 3D metal-oxides, which have strongly correlated electrons, the electrons can interact with the lattice. That means, we know that at non-zero temperature, finite temperature, there will be lattice vibration, which we call phonon. Then electron can couple with the phonon, and that coupling together, we call them polaron. These are quasi-particle. Pictorially, if we look at this figure, electron can be trapped due to lattice distortion. This lattice distortion creates enough negative potential or a kind of a potential well to trap the electron. And this shaded area is kind of a indication of the extent of the wave function for this electron and phonon coupled state. In terms of the extent of the polaron wave function, this can be divided into two with some obvious name. If the localization is less than the lattice parameter of the unit cell for a crystal, we call them small polaron. Sometimes it's also called Holstein polaron. And if the extent of the wave function for the polaron is larger, it could be larger than few unit cell, then we call them large polaron or frolic polaron, because those two names, they made the mathematical model for these two polaron, which we have a very quick review in the next slide. Just to give an idea that why we are calling this thing or related to transport property. If we consider diffusion length, silicon has diffusion length in order of 100 micrometer. Tungsten oxide, which is not strongly correlated 3D oxide, it's 5D oxide, it still has larger electron diffusion length, 400 nanometer. On the other hand, if we consider the oxide, which has 3D electrons, Bismuth vanadate with vanadium, iron oxide with iron, as you can see, that the electron diffusion length decreased significantly, 75 nanometer and 2 to 4 nanometer. This small electron diffusion length, in other ways, we can call that, or you can say that these have very high resistivity. These are the consequences of polaron formation. This polaron can only hop from side to side to conduct electricity. And hopping, as you can understand, that hopping means not only the electron, also the distortion is transmitted with it. Hence, the charge transport is very slow. A quick history of polaron. Polaron, the concept was first introduced by Landau in 1933, and then Pecker in 1946 just modified this model and then published a paper, which is usually called Landau-Pecker model. This model is developed by considering dielectric continuum. Don't get into the solid crystal or the band model of the solids. Frolic, on the other hand, he based on the Bloch equation, apply the second quantization to write the Hamiltonian for polaron, where the first summation is the contribution from the particles, electron or holes. Second one is from phonon, and this is a linear coupling term between the particle and the phonon, electron or phonon or holes and the phonon. The V term, which is the coupling, which signifies the strength of the coupling, this is taken as a long-range average within certain volume V. Here, alpha is the electron-phonon coupling constant that is used in here. It's a dimensionless quantity. Small polaron, that model was proposed by Holstein. It's a similar Hamiltonian. The only difference is that instead of this VQ, this has G and N. G here is a short-range electron-phonon coupling, and this N is the number of unit cell used in the calculation. Now, the computational methodology that we have used in our work is density functional theory with Hubbard kind of U electron repulsion energy. This is added to localize the electron on a certain site. How we did it, it's a very easy process. Let's say this is a ground state crystal, which is a bismuth vanadate. We can add electron or a hole to this unit cell to ensure that this extra carrier gets into a preferred position. That position can be perturbed slightly, and then it can be relaxed fully. If we add an electron, we get electron polaron. The localized wave function can be seen in here. or if we add a hole by taking out an electron, basically, then that creates a whole polaron, and that can be localized if in metal oxide at the oxygen side. All the calculations were done with the fast code. We will start with bismuth vanadate. Hence, this is just an introduction slide of bismuth vanadate. We checked the crystal relaxation and everything. As can be seen in this table, our calculated lattice constants are agreed pretty well with the experimental ones. There are many other experimental work. We just pick one. Now, this is a band structure. After relaxation, we calculated band structure for bismuth vanadate. The feature that I would like to point out in this density of state plots, the valence band maxima, as you can see here, these are mostly composed with oxygen p orbital, and the conduction band minima, these are mostly composed with vanadium d orbital. Now, why I'm pointing out this? Because when we localize or stabilize polaron, we know that whole polaron will be stabilized near the valence band. So it will create it mostly on the oxygen, include oxygen p orbital, and similarly electron will have vanadium d. So this kind of information immediately tells us that which orbital will be involved in polaron formation. Now, in bismuth vanadate, we also quickly calculated some of the features, the electron effective mass. And electron effective mass for bismuth vanadate without any doping is around at least 2 times more than the rest electron mass. That means 200% more than electron effective mass. We try to do manipulation with pressure and some delocalized doping. We can reduce up to some extent, but not too much. These are the experimental indications. I think I will not go into the details of it because of the time. This tells us that there are some possibility of forming polarons in oxides. So basically, we ask this question that can we confirm polaron formation in bismuth vanadate, and then how it affects the transport. First, the way we mentioned, we localize or we stabilize electron polaron, and as expected, it stabilized at the vanadium site. The charge state of the vanadium ion changed because of electron trapping in the lattice, and this shows the lattice distortion, which create the potential to trap the electron. Then we look for the electronic signatures. This is the DOS plot with the band gap for pristine bismuth vanadate, and this is electron stabilized or electron polaron stabilized density of state plots, where the polaron state, as you can see, is created about 0.4 electron volt below the conduction band minimum. Then we tried on bismuth. This is just a test case to see if something happens with bismuth, but something happens. Yes, we see some unoccupied states just above the valence band, and the wave function of the charge density is perfectly spherical, as you can see in here. These are basically bismuth 6s orbital, the anti-bonding 6s orbital that presents on the top of the valence band. And this is not definitely a polaronic band. This is just some kind of pseudo-metallic structure. Then, of course, on oxygen side, we tried the the whole polaron formation. We stabilized hole in one of the oxygen site. As you can see, this only oxygen site shows this localization. None of the atom has the contribution. And it's from the look of it, we can see this has the oxygen P type of character, the dumbbell P type of oxygen 2P character. Then also we calculated the electronic signature. We have found that the polaron formed about 0.8 electron volt above the valence band. This is the polaronic state. Now we compare our results to the experimental results. These experimental results were from our colleague in Darmstadt University in Germany. So from our theory, what we have found that the electron polaron formed at 0.4 approximately from conduction band minima and valence band minima. The whole polaron created about 0.8 electron volt. If we compare the numbers, 0.38 versus 0.3, 0.80 versus 1.02, I would consider them, these are good agreement given the fact that DFT does not have very good reputation in reproducing a strongly correlated system. But for the polaron, the modeling technique we have used serves us well. This is the published figure. I just copied it from the paper. Now, because in polaron conduction, one of the important things, when polaron hop from side to side, there is an energy barrier. We call it activation barrier, and we calculated activation barrier for both electron and hole polaron. When the polaron hop from one side to another, it goes through this activation barrier, and the calculated activation barrier are shown in here. This is the whole activation barrier, about 0.3 electron volt. Electron polaron activation barrier, about 0.4 electron volt, which shows that whole polaron will be more probable in bismuth vanadate than electron polaron. In fact, several recent experimental papers, not within our collaboration, has shows this feature. Then we calculate polaron mobility. For polaron mobility, we use an empirical formula. It's called Einstein mobility formula. For this, what we needed is this frequency we knew from the lattice, so phonon frequency. So we calculated the phonon frequency dispersion and the phonon density of states. We know that whole polaron stabilize at oxygen. So you get the oxygen characteristic frequency, and electron stabilize at vanadium, get vanadium characteristic frequency, and calculated this to mobility. Electron mobility and hole mobility, as we can see, consistent with the activation barrier results, hole mobility is higher than the electron mobility. Just to put things in perspective, if we consider silicon, the mobility of charge carrier in silicon is 100 to 1000 centimeters squared per volt per second, where these are, as you can see, in micro level, 0.3 times 10 to the power minus 6. So these are almost 1 million times smaller, the mobility, and hence polaron creation does create problem in terms of transport property, as well as performing those catalytic properties that we started to improve. Just one slide, we also calculated for delphosite materials, copper iron oxides. We compared the theory.
Sorry,
yes.
Dr. Nurlada, you have 2 minutes left. Sorry. For this.
I have only one slide left, so I'm done.
Okay, thank you very much.
Anyway, so from the copper iron oxide, we calculated the polaron in here. And this figure summarizes our calculated and experimental results together. We are not as successful as we had in vanadium oxide, or bismuth vanadate. As you can see that we get the electron polaron created at about 0.55 electron volt. No, sorry, we had problem with the whole polaron, but the electron polaron was pretty good in here. 0.55 electron volt versus the experimental value of 0.6 electron volt. But for the whole polaron, we did not get good correspondence. Now, this is the conclusion slide. We basically have found that polaron usually forms in a strongly correlated system, especially in 3D transition metal oxides and 4F rare earth oxides or sulfides. Polaron formation is very common. Polaron conduction is different from the band conduction. Band conduction is represented by the band feature of solids. For example, materials like silicon, gallium arsenide, zinc oxide, they have pretty much band conduction. One of the most popular oxide, titanium dioxide, which was the first one almost 50 years ago, was shown for this photo-electrochemical process that also has polaron conduction. So polaron is a coupling between electron or holes with the phonons. Electron-polarons form below the conduction band minima on the cation side. Hole polaron forms at the anion side above the valence band maximum. Now, this feature I did not discuss today because of time constraint. We have shown, and this work is published, that the polaron gap, the polaron state for the electron and hole, they create a polaronic gap within the band gap. And that gap actually determines the photoelectrodes photovoltage that we know. Final point is we're in search to find a mechanism to suppress polaronic states from within the gap. We have some initial results from our California collaborators, which are showing promising indications. Lastly, I would like to acknowledge Texas Advanced Computing Center for the computing time and National Science Foundation for the funding of this work. Thank you very much. I really appreciate the opportunity to present my research. I am now open for questions, if there is any. Can you hear me?
Yes, I think sir, Professor Dr. Ghulam Mohammad Buhera is here. Sir, please, can you unmute?
Oh, I see. Sorry. Thank you. Sorry. Oh, thank you. Thank you very much, Dr. Huda, for your excellent presentation. And now the floor is open for question, comment, or any discussion. Okay. Is there any question?
Sorry.
Sorry. Hello?
Sir,
okay.
may I ask one question? Oh, thank you for your nice presentation. Actually, I just need to do a simple question. Your methodology. So, if you're not just adding one electron or just hole. So, in case of if you add one electron the system and optimize, maybe the structural change should happen, and just like as a UV irradiated system. Am I right?
Yes, of course, you're right.
So in that case, what types of any effect of this result?
Okay, let me go to the slide. If I can go quickly, sometimes I think, yeah, we are almost there. Let's go to the next slide. Yes, for example, in this slide or in this scenario, a hole is created on a certain site. Of course, how do we create hole? We basically take an electron from the supercell. So this is a 2x2x2 supercell of bismuth vanadate. We take one electron, that means we create a hole, and then we make a slight perturbation on one of the anion side because we know it will be created on anion. If we do that, then of course we imbalance the forces within the system, between the ions. And then we relax it completely. When you relax it, then this happens around this side. So these are the lattice distortion. We also mentioned, I did not go through in detail. For example, the vanadium oxygen bond length, the equilibrium bond length was 1.74 angstrom. But after the relaxation, that bond length, as you can see, this oxygen and vanadium over here, this bond length is now extended to 1.84. Similarly, bismuth oxygen bond length was 2.50. Those are also changed depending, not uniformly, it depends which direction we are getting for the bond. So yes, there is a distortion. In fact, this local distortion where the hole is trapped now, that facilitate this charge trapping. But if we come far away from that localization point, let's say a suitable point where we are not even close to the periodic image of that site, then the deviation of the bond lengths from the equilibrium bismuth vanadate bond lengths are negligible. But yes, we do need to relax it completely. One more point, which is slightly more detail of the methodology, is that because we are adding or taking out electron, this is a charged supercell. And because of the infinite nature of periodic boundary conditions, it will be an infinitely charged system. The technique is to add a background charge density so that that artificial infinite charge is can be neutralized.
Thank you very much.
Thank you. I'm not an expert in this area, but I have a small question for you. Is the polaron and polariton same thing or different thing?
The polaron is just what this is. It's just a electron or hole get trapped due to the lattice distortion.
Yeah. Okay.
And they create kind of a negative potential. So that's all is polaron, nothing else.
That's it. And polariton?
I don't remember right now about polariton, so I would not guess it.
Okay, so now just my question was that is there any interaction between polaron and polariton? No. Okay, thank you very much. Okay. If there is no more question, then
sir, I have a question, sir.
Okay, ask.
Thanks for this wonderful presentation.
hand raise করে আছেন
Asi, okay. Allow them to.
প্রথমে ইমতিয়াজ আহমেদ
Thank you, sir. Thanks for this wonderful presentation. I have just one question. That you are using this DFT plus U approach, right, to calculate the. But usually in the literature, people use like the post-DFT method to analyze this sort of polaron, because these are kind of excited states, and DFT always go for the ground state calculations. What's your comment on that? Do you have any plan to extend your work like GWs or some other methods for more accuracy? Thank you.
No, thank you very much. It's a good question. For this particular type of calculations, we don't need to go GW. One of the problem with GW, or two problems. One is that it is a very expensive calculation. And second, those are not variational, meaning it just calculates one step single point kind of energy about band corrections. Hence, if I want to stabilize polaron in a crystal, the GW, we have to first get the structure, the polaron containing structure, and then I can apply GW just to get the, you know that GW is basically pseudo particle corrections, many body corrections on that particular sense, but it is not a total self-consistent energy calculation. So it will not give me, let's say, that activation energy that I have calculated. I shouldn't say we have calculated, or the mobility in that sense. If I want to, let's say, I'm only interested to the correction of the band gap or the exciton binding energy, that exciton is broken for electron or hole mobility, then GW would have been a better method. Yes.
And what about the hybrid? Why don't you try hybrid like HSE06 to get a more accurate description?
We did hybrid on many other materials. For this particular one, to localize this electron or hole at a certain site, hybrid doesn't do well. It tends to localize things at arbitrary position. And also hybrid for this large supercell is extremely expensive calculation as well. But we did try hybrid and did not. One of the good thing about DFT plus U, despite tons of limitations, is that we can use DFT plus U in a very preferential way. And also nowadays we can calculate U in self-consistent manner, not like as a parameter.
Thank you, sir.
So may I ask you a question? Yes, sir. Okay. So yeah, Shamsbhai, can I proceed?
Yes, it's your turn.
Okay, thank you very much. Okay, thank you very much for your nice talk. Just for photovoltaic water splitting, either by photochemical or photocatalytic, whatever you say, the effective mass of hole and the effective mass of electron, that this ratio actually play a good role to reduce the recombination rate of charge and hole, right? So it is so far it is believed that from the theory of Zhang et al. Published a paper in 2012. So they are this is so far the established theory. They are saying that the ratio of the whole effective mass of hole should be much larger than the effective mass of the electron. But is it not always also true in the other way? The effective mass of the electron would be greater, and their mobility will be higher, and the separation will be larger, and their recombination will be less. So do you think that is it not possible? Also, is it not expected also in the other way? Right? What do you think?
It has to be. It has to be. Most of the common experimental work that I have seen so far are considered metal-oxide photo-electrocatalyst as photo-anode material. In that sense, the first scenario that you have mentioned, that electron mobility should be better, as meaning it has lower effective mass and hole should have higher effective mass. That kind of scenario can be considered, even though I'm not very supportive of this kind of a statement because of other reason. We have considered those things theoretically as well. But if we take that argument for granted, then if we get a photocathode, but unfortunately in metal oxides, there are not much metal oxide that can work as a photocathode. People tried using copper oxide, Cu2O, Q plus oxide, but Q plus oxide has a problem with spontaneous copper vacancy formation. It makes it a degenerate semiconductor. So it cannot be used. Recently, we published a paper on a quaternary metal oxide, copper, bismuth, tungsten oxide, that can be, and that experimentally verified our prediction of the materials, that can be used as a photocathode. So when we get photocathode, then you should think of the other way, because now majority carrier will be holes rather than the electrons.
So recently we did an experiment actually on photocatalytic water splitting, not for photo-electrochemical. And here we used the cesium tin chloride. And according to theory, right, we should not get any photocatalytic water splitting for cesium tin chloride. But we certainly found both by using ultraviolet light, but also using UV visible light, we could degrade the rudiment B and we could successfully split the water, right, and produce the hydrogen. So then I think that yes, we should propose the modification of this established rule, what they said.
Yeah, I mean, sometimes I have seen those kind of statements. My always question is, if someone tells me that electron effective mass has to be higher than the whole effective mass, then my question is why?
Exactly.
And then definitely we'd explore those scenarios. And if we calculate from excited state point of view, if holes are slower than the electron, meaning hole effective mass are the higher, then because the recombination takes place within picosecond time limit, the electron hole recombination is higher. So it's my understanding, and I worked with John Turner in National Lab as a postdoc, and you can find his seminal work in photo-electrochemical water splitting. So my understanding and my work also shows that electron and hole should have comparable mobility. Exactly. So that because minority carrier has to move, other than I cannot get the second half of the reaction.
Thank you very much. I think we should propose for the others.
Sir, Professor Nokib হাত তুলে আছেন কিন্তু সময় কি হবে মানে
Thank you very much. Thank you very much. Thank you very much. So actually, I have one comment and one question. The comment regarding the effective mass is that you have the dispersion relation. You can calculate the effective masses, right? So have you tried to do that?
Yes, we did. I think there is a plot in there where, because of time, I went so quickly. Let's see if I can. Here you go. So this one, for this one, effective mass, there are two lines in here. One, it says without pressure. So the effective mass of bismuth, pristine bismuth vanadate electron effective mass is 2.05 times ME. M is the rest mass of the electron. And then what we did, we started applying hydrostatic pressure to see if pressure has any effect, because we had a collaborator in a national lab who had this diamond and well high pressure experimentation facilities. So for that reason, we calculated the electron effective mass with pressure. And then also we doped niobium, which has 4D electron. We take out some of the 3D, replaced by 4D niobium, and we see that effective mass dropped even further. Still, as you can see, effective mass is higher than almost 1.5 times the electron rest mass.
Okay, so yeah, good.
No, it is just.
Yeah, I'll just.
Time maintain karo.
Okay, so actually it should be the bare mass, right? Not the rest mass, if I am correct.
Well, the bare mass means, yeah, meaning bare mass in the Schrodinger equation there, so Kohn-Sham equation.
Yeah. Okay, so my next question is, for the formation of polaron, you need quite strong coupling between Charge degrees of freedom and lattice degrees of freedom.
Definitely.
Yeah. So have you made any attempt to calculate the electron phonon coupling constant from the transport sense?
Well, when we use this, not explicitly, but it can be done because we calculated almost every possible things that we can do from this kind of ab initio method. So
yeah, that is why I was asking, because that would be a useful parameter to know, I think.
Yeah, because you know,
thank you very much, because we are running out of time.
Thank you very much. Thank you very much.
And also, I'm happy to talk with Dr. Naqib, I think after 20 years.
Yes.
Over telephone.
Yeah.
Email. You can communicate.
Nurul Huda bhai, it's very nice to see you. Yeah.
Thank
Good
you.
to talk
Thank
to you
you,
as well.
the invited speaker, and for your nice talk. So we have to move to the contributor talk papers.
Thank you.
Now.
So stop sharing right now.
Okay.